So my report is all about the preliminaries and the binomial theorem. So first, preliminaries, theorem 0.1, well ordering principles. This principle is considered as an axiom in number theory. In many other results, we use these well ordering principles to prove that results state that every non-empty set S of non-negative integers contains at least element, or we can say that there is some integer which A belongs to S such that A less than or equal to B for all B's belong to S. So we can say that S is a set of non-negative integer, and it always have a smallest element, and we do not have a proof for this principle. We assume that this fact is true, and assuming this is true, that for every set which is a non-negative integer, if we can show that this set is non-empty, so as long as we can prove that it is non-empty, we can say that has a smallest element. Theorem 0.2, Archimedean property. So let us first prove the Archimedean property. So let me first give the statement of this Archimedean property. It says that if A and B are any positive integers, then there exists a positive integers n such that na greater than or equal b. Now, to prove the Archimedean property by contradiction, I'm going to assume that the statement is not true. So assume that the statement of the theorem is false. So I assume that this theorem is false. So if I assume that the statement is not true, so then I will consider for some A and B belong to positive integers. What I assume is that NA is less than B for every N which is a positive integer. So I have considered N also a positive integers, and we say that false exists in positive integers. Thus the set S is non-empty because we have considered the selection as n times A less than B for all n where n belongs to positive integers. So when S is a positive integers, I can apply consistently of positive integers. So I can apply well ordering principles. So by well ordering principle, and this principle suggests us that we can have at least element in the set S. And now the last element is B, M, A. So M obviously belong to positive integers. Also note that whenever M belong to integers, M plus 1 also belongs to integers. So we can note that B minus M plus 1 times A also lies in S. However, B minus M plus 1 times A, this is the same as B minus MA. And this whole quantity, this B minus MA, because we are subtracting A from this side, from this side, now we got a smallest element, b minus ma. And this element b and this b minus m plus 1 times a, this belongs to the set of S. So all the elements b minus na, whenever n is a positive integers, it belongs to the set S. So we say that m plus 1 is positive integers, so definitely this element must belong to set, but this is the smallest BMA, so contradicts the fact that b minus ma is the smallest element in S. Thus, our assumption is false. Therefore, if a and b are any positive integers, then there exists a positive integers n, such that n times a greater than or equal b. So next, theorem 0.3, first principle of finite induction. Let S be a set of positive integers with the following properties. So first hypothesis is the integer 1 belongs to S. And second hypothesis, whenever the integer k is in S, then the next integer k plus 1 must also belong to S. Then S is a set of all positive integers. So proof by contradiction. So let T be the set of all positive integers not in S. So let T be the set of all positive integers which are not in S. And we assume that T is not empty. It's not empty. So according to well-ordering principles, T contains a less element, say A, which we denote as A. So because using the first hypothesis, this first hypothesis 1 belongs to S, this implies that A greater than 1. Because if a less than 1, then this won't be 0 positive integers. So this hypothesis 1a belongs to S implies that a greater than 1, and also implies that 0 less than a minus 1 less than a. So we mentioned that a is the less or smallest element of T. This implies that a minus T minus 1 does not belong to T. So this implies that a minus 1, hence a minus 1 belong to S. That's from the hypothesis 2. According to hypothesis 2, S must also contain a minus 1, a minus 1 plus 1, which equals to 1, then a which equals to a, where a is belong to S. So this is contradiction. Means our assumption that T is a set of positive integers which are not in S, and assuming that T is non-empty is not correct. So this contradicts the fact that A belongs to T, therefore T is empty, and so S contains all the positive integers. That's the end of proof for first principle of finite induction. Theorem 0.4, second principle of finite inductions. Let S be a set of positive integers with the following properties. So first principle and second properties have the same properties. So A belongs to S if 1, 2, no. Sila, yung hypothesis 1 lang sila nagkapareho. Din yung 2 is if 1, 2, k belongs to S, then the next integer k plus 1 must be also belongs to S. Let's have an example. So suppose that the numbers n are defined inductively. So by a sub 1 equals to 1, a sub 2 equals to 3, and e sub n equals to n minus 1 plus a sub n minus 2 for all n greater than or equal 3. Use the second principle of finite induction to show that this a sub n less than 7 by 4 power of n for every positive integer n. So the resulting sequence of numbers formed by a sub n is this, which is called locus sequence. So first sequence is 1. So 1, and second sequence is 3. We cannot do anything about that. But 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, 7 plus 11 is 18, 11 plus 18 is 29, and so on. So that's the local sequence. So except for the first two terms, each term of sequence is the sum of two preceding two, so that the sequence may be defined inductively. So if we're going to so we know that a sub 1 equals to 1 clearly, and similarly to a sub 2 equals to 3. So this we can say that this is our formula for all n, and n is greater than or equal to 3. So what we need to prove here is this. Sorry, actually this is power of n. So we intend to prove this upper bound for the locus sequence, and to prove this I will be using mathematical induction second principle. So n equals to 1, then we know that a sub 1 is equals to 1, and then 7 by 4. So yung n natin dito is 1, so 7 by 4 na yan, hindi na ma-change. So which is true because a value is 1, as we can see that, and this value that we have given as an upper bound, so the result is true. So this is true. Then the second, for this, let n equals to 2, so we have, so a sub 2 less than 49 over 16. We know that a sub 2 equals to 3, and then 7, 4, yung n natin is 2, is equals to 49 by 16. So thus, it is true for n equals to